Thank you. Thank you for the invitation. So it's nice to be here. I don't think I have ever spoken in this conference about work that's published. It's always something that's like cooking up. And today it won't be the exception, but at least I can give you guys a little sneak peek of what we're thinking. And this is work with Hui Tran, a student at Harvard. Is it here? Okay, he should be here. And Uriko, who's my friend at CMSA. And it goes by the name of an exact black hole scattering amplitude. Sorry. How do I? Sorry, should I move the? No. No. Oh yeah, great. The point I want to submit to you guys today is that we should think about the self-dual sector of amplitudes as a kind of bosonic version of supersymmetry. So we heard yesterday that it would be a good idea to harness all the power of supersymmetry, super Young-Mills, amplitude hedrons, and all of that beautiful constructions to down-to-earth QCD amplitudes at any loops, especially something like all class amplitudes that live in these very restricted sectors. And there are many reasons to view self-dual gravity and self-dual Young-Mills in this way. So let me give you a few. We all know, mainly from a few years ago by Montero and O'Connell, that the self-dual sector exhibits very beautiful extended symmetries. So there is a notion of integrability, but more precisely, there's a notion of what these higher spin generators are. Sometimes I go by the name of W algebras. And perhaps also very important in this context is that there are certain solutions in supergravity that we get from M theory or 10-dimensional supergravity that happen to reduce to 4D in a very beautiful way. And they become, from the 4D perspective, you only see the polarizations of these gravitons, and they happen to be plus polarizations. Okay, so there are some self-dual theories in that regard. Perhaps less known is that there are spot integral calculations for amplitudes that actually localize. I'm going to talk about that a little bit more. And I shouldn't have to convince you guys that there is a very nice underlying structure in all these self-dual sectors. When you perturb slightly from self-duality, you get things like the Park-Taylor formula in a self-dual background, or the Hodge formula, and of course, much more. I actually had a recent work with Nora Miller and Mina Hingwich at IIS recently on how to construct Hodge's formula from all of these extended notion of symmetries, so-called W symmetries. But today I will mainly focus on these 2 points. The notion of self-duality is a bit more flexible than supersymmetry because it allows from a small perturbation. So there's a continuum of sort of continuum spectrum of self-dual or near self-dual theories. So self-dual actions can be perturbed. I'm hoping we will hear more about this in many of the talks in this conference, but let me just go by the slogan of the nonlinear graviton theory that perturbs self-dual backgrounds. But what I want to emphasize what I want to emphasize today is that this phenomenon is actually close related to a phenomenon we understand in black hole physics. So this being an Amplitudes/GR conference, I would like to introduce this connection here between self-duality and extremality. Okay, so with these half-an-hour talks, I always get very anxious whether I'm making a good point or I'm just derailing in the details. So I just decided to give, for now, just 2 punchlines, and then you guys can dig up and do more important things. So the first of these 2 punchlines is that we will present a new O'Connell formula. In a case where we take a background, take any background you want, maybe Kerr with a spin and a mass and a charge if you want, and then add this extra parameter we call the NUT charge. This is an exact solution of general relativity. It's called the tau NUT sometimes, Kerr tau NUT, Plebansky-Demiansky, and so on and so on. And once you add this NUT charge, we can essentially resum the full O'Connell expansion, sort of non-perturbative, in a formula that may look familiar from some of the previous talks, but has a phase that's sort of asymmetric with respect to the direction of the NUT charge. And this phase depends on parameter Q. Q is 2n omega. If you think of n being sort of similar to m, the mass of the black hole, so it's kind of the magnetic part of that. This expands into a correction that looks like Gn omega. So it's kind of all the Pons-Minkowskian content here that's resum. It's essentially the angular problem of this background that's fully resumed in this phase. And so we plug the amplitude, the favorite radial action here, and we get an amplitude. Importantly, when the mass is equal to a not charge, we call that the self-dual point. And in that case, this little expression here solves the Teukolsky equation exactly for a background of spin A, and mass m equals m, the not charge. And because it does so, it has a discrete spectrum. If you were to actually write down the Teukolsky equation and compute the normal modes, it would be actually normal, not quasi-normal. And you would find that those modes actually become exactly the same as the hydrogen atom. That's why we call this, with Uri, we call it in 2023 the hydrogen atom of black hole. Okay, but perhaps more importantly is that if you have a black hole, you have these quasi-normal modes, right? So you have absorption, this kind of the elephant in the room in all of the EFT framework. But how do we actually record this with something that looks just like a hydrogen atom that actually doesn't have any dissipation? Well, the second punchline is that near the self-dual point, so when m is of the same order than n, but not exactly that, we have something that looks like a self-dual solution called the Eguchi-Hanson solution. It's an infinite throat that sort of blows up the horizon of the self-dual point. So the self-dual point doesn't have a horizon dissipation or anything, but near it, it actually has an infinite throat in analogy with the extremal case. And in this infinite throat is where this quasi-normal mode lives. So you can essentially do a matching computation. And not surprising, it's controlled by an SL2R because it's super symmetric. I mean, it's highly symmetric. And that SL2R happens to match what people have recently called the love symmetry. But perhaps more interesting to this story is that this Eguchi-Hanson is actually what generates these quasi-normal modes when you glue it to the self-dual point. Okay, so those are the two remarks. You may decouple now and attend more important matters. But if you are still interested in this talk, I'm just going to continue and explain to you, because maybe you don't care about nut charges. Maybe you think, oh, nut charges do not exist. It's a Misner string. There are causal problems, closed time-like curves, and all that. So we're never going to look at these kind of things. So let me try to advocate that actually nut charges do exist, and they are realized in nature, as long as you assume that Kerr, the spinning black hole, is realized in nature. And hopefully you believe that most astrophysical black holes are Kerr. So if you take the Kerr solution, suppose you add a nut charge. It's just natural, but if you don't like it, just set it to 0. You can still, in any case, look at the extremal solution when the parameter A is very close to this combination of mass and nut charge. And near the extremal solution and near the horizon of the Kerr black hole, where two of the horizons coincide, you find that there is an extended isometry group, which is warp IDS3 QC1, that happens to be a tau knot metric. And it's a special tau knot metric where you exchange, I haven't told you what the signature is, but essentially you exchange the mass and the knot charge of the Kerr black hole with the mass and the knot charge of the tau knot. So for instance, if you start with some Kerr black hole that has no knot charge, as you may like, on the near horizon, you end up with a tau knot that has no mass, and it's only a pure knot solution. So that sort of tells you that these knot charges are there just because of the near horizon of black holes. And in fact, you can see that the case which is self-dual, where n is equal to m, actually it's sense to himself is self-similar, which means essentially that this self-dual solution has no horizon, as I just explained. There's only it's a single point. So actually, in the self-dual case, there is no near horizon. But once you accept that tau knot exists, and you accept that this is a self-dual solution, then there are many more interesting solutions that happen to live in this realm. And in fact, Gibbons and Hawking actually have a solution that's static, but has like multi-center singularities, and you can actually play with them and actually give them a little momentum and see what happens. So there's like a lot of rich structure once you accept that these self-dual solutions do exist. So of course, Kerr is always lurking in the background in all of these ideas. So what I want to do essentially today is to try to explain some of the striking properties of Kerr's black holes from the perspective of these toy models. If you wish, you could think of them like that. There are many interesting properties I don't have time to describe. There is something called the Kerr separatrix. It's something that happens in phase space. There are analytic quasi-normal modes, but let's just move on for now. The point is that we sort of get inspiration of constructing these toy models from something that looks like supergravity reduced on some manifold. So just to give you a flavor, you can think of BPS states in supergravity. You take your M theory, compactify on some Calavillao, it could be a torus, a 6 torus if you wish. And then you essentially look at these 6 branes that are essentially wrapping this torus. And what you find is that from the perspective of 4 dimensions, they look like these point particle singularities. And they are self-dual in the 4-dimensional case, but they are BPS in the higher dimensional sense. The space-time that they source is scalar, which is cool. If you heard some of yesterday's talks, scalar spaces are nice. You can do calculations in them. But it's sadly trivial. They don't actually move because they are BPS, so there is a cancellation between them. So not much is happening. To make something happen, you actually need to perturb this slightly away from, again, this notion of perturbing the self-dual solution by adding something that's not a BPS. It's a D0 probe, so it's just a word line if you want. And in this word line system, you find that there's a coupling between the D0 and D6. If there's many less the zeros than the 6, that's kind of a probe limit, but you can actually perturb and get something that looks more like a self-force sort of average mass ratio between N0 and N6. Okay, that's a supergravity story, but actually we don't need to talk about that. We can talk about the bosonic case. So in 4 dimensions, nothing supersymmetric or anything. Just consider the analog of that D6 defect is a simple Misner string. It's a thing that carries the not charge. So there's a particular defect that sources a field tensor that's self-dual. And because it's self-dual, we call it BPS just because the electric and the magnetic component cancel. And in this defect, well, again, they don't interact if you put them next to each other. But if you put a sort of anti-self-dual defect that couples to this field strength, then you find there is a nice interaction. So in other words, if you have 2 plus gravitons, they don't touch each other. But if you have plus and minus, then you can propagate that. That's some sort of the simple version. This is related to a double copy, as I learned from Jung's nice paper. Okay, so that motivates me to understand what are these perturbations. So I just said that if you take a plus and a minus graviton, they do interact. With Andy, actually, we constructed the space-time solutions for tau naught, starting from these 2 3-point amplitudes. And obviously, one cancels when the mass is equal to not charge and the opposite here. But then you can try to make them interact via what people have been calling the Compton amplitude. So in this Compton amplitude, you have a source that gives a plus graviton, and then there's a anti-self-dual graviton that sort of couples to it. At the very leading order, you will find a contact term. And that is sort of a trivial calculation. We studied. You can solve the many constraints that this have. You can add the contact terms. So let me just try to focus on this. So I would like to advocate that this is kind of an anti-self-dual photon ring in a self-dual background. Now, how do we understand that? OK, so the convenient way to calculate Compton amplitudes is through the wave equation, sometimes called the Teokovsky equation. And you can take your favorite background. I'm talking about self-dual case, but if you take the generic one, has 3 parameters: mass, not charge, and spin. And then try to solve the wave equation in that background for a scalar, diagonalize it in terms of eigenstates. Those happen to be called monopole harmonics. They have a not charged Q as compared to the normal spherical harmonics. And so the background actually has a not charge. There is some energy in the scattering. So there's a component of the amplitude that looks like this. It turns out that you can take this full amplitude, which is kind of doing a pad integral, and then sort of take a saddle point approximation of this pad integral. You take the asymptotic expansion of this. You literally write this monopole harmonics as a pad integral and take the asymptotics as a saddle point and find that the full series resums into the Aconite formula I showed at the beginning. There's a little caveat. So here it's kind of equatorial scattering, if you know what that means, but in the presence of a not charge that happens in a cone. And this was nicely addressed by Don and Uri before. And this formula, as I said, happens to be exact for the self-dual case, but you can still compute this radial action, as you know, away from the self-dual point. You can compute it from Churchill if you want. And it just happens to have some close expression. More importantly, you see that you can read off the quantization spectrum from the WKB here and find that at the self-dual point, because there is no precession, the spectrum is degenerate. So this goes back to the idea that this is the hydrogen atom. So I'm proposing that this is the starting point as a perturbation expansion in the same way that we perturb the hydrogen atom by a fine structure constant. Okay. So in the second part, how much time do I have? Yeah. And the last part of this talk, I want to just literally do that. I want to perturb away from this self-dual black hole solution. And the way that we do that is that we think of the black hole as some sort of critical system. So if there was a notion of temperature, like in holographic systems, there is something that happens when the temperature goes to 0. There is new emergent symmetries, there is a scaling variance, and then there is like all kinds of integrability conditions. But I haven't told you exactly what the temperature is in this game. Let's just go back and understand the case that's more well understood, which is the near extremal charged black hole, so Raison-Nostrom solution. When the charge is equal to, this should be the mass. So when the charge is equal to the mass in a Raison-Nostrom solution, there's an ADS2 throat near the horizon. That ADS2, maybe you don't care, it's related to chaos and all that. More importantly, it controls the quasi-normal modes. So again, this thing controls the absorption near the horizon. There is a 2D dilaton gravity theory that lives in here. That computes for you the entropy of the black hole, but if you don't care about that, it computes the quasi-normal modes, which is sort of the thing that maybe it would be important to match to other calculations. And well, then there's the extensions of this story where instead of having an electric charge, there is a spin, and then this has been sort of extended by Dan Capet and collaborators. But more importantly, sort of the upshot is that we can compute things from this throat here. So that's kind of the thing I want to push forward in this case. Okay, so let me introduce a nut charge. So actually things become simpler now. I define for you this temperature is a dimensionless parameter. It just tells you how far you are from the self-dual point. This is defined 2,2 signature. I'm not going to go into details, but there is a analytic continuation here in the nut charge. And essentially proportional to the Hawking temperature if you were to do the computation very carefully for tau nut. So I define this temperature. I'm going to study what happens when the temperature is very, very low. So this black hole is very cold. The two horizons of the black hole in the 2,2 signature, not the same as the event horizons. They actually coincide as the temperature goes to 0. So this defines a critical system where the photon ring shrinks at the rate that goes like t to the 2/3. These 2/3 I circled because it's the exact critical exponent we get in fractional Hall effects. And it just sort of highlights the fact that there is a critical system here. But what is the photon ring? Well, in this case, the photon ring is just the unstable maximum of the potential of this system. You can see that as I shrink it, as I go to this self-dual point, m equals to n, actually this unstable maximal point disappears. And I just have this unbounded von Breilau spectrum of the hydrogen atom, and everything is non-dissipative. Right? So I don't have any quasi-normal modes. But as I turn it on slightly, so I actually become, there's a potential wall here that gives me quasi-normal modes of Schwarzschild. Okay. So this all goes into a very similar story to the charge case. As you take t going to 0, you can zoom in into the horizon. There's a region where x is sort of the order of t. In that region, all the way to the horizon, you find the Eguchi-Hanson metric. This is a self-dual solution. It's very simple. The wave equation in the Eguchi-Hanson metric is just the law of symmetry equation. Away from the horizon region, x order 1, you find the self-dual solution. Again, it's also very simple. And essentially, you do a matching computation between these two regions to compute dissipation. So, I've been mentioning this photon ring, and given that I have sort of a few minutes, I can, then I can explain what the photon ring is, because I just sort of hand-wavingly describe it. So this is the interpretation I want to push forward here, is that the photon ring actually emerges from some kind of discontinuity of the radial action. A photon ring is what happens when you throw in a photon that goes around many, many times. So if you were to compute a scattering angle, a very, very small impact parameter, you will see the scattering angle winding around the black hole infinitely many times. In fact, people computed this from Schwarzschild. They found a logarithmic divergence in B. And you can understand this by the fact that the radial action that has been discussed before in this conference has a discontinuity. Okay, discontinuity simply happens because as you cross this potential barrier, you actually add a piece to this radial action that comes from the potential well. So it's simply because after certain impact parameter, you end up getting out of this potential well, and that gives you a discontinuity here. And what's trapped in this potential well, on the other hand, is this resonance. So here I'm sort of connecting the notion of what the resonance is in the potential well to this continuity of the action. This is the phase shift that you will find a small spot at small scattering angle. And they are all related, of course, because the action on this potential well is essentially the decay width of the resonance. Okay, so we can see this explicitly in this self-dual case. It's a general phenomena, but for the self-dual case, as I take the temperature, the self-dual temperature to 0, again, I'm lowering down this potential well, and I'm sort of accessing this region. I can compute the tunneling amplitude, the amplitude that allows me to escape this well. That's an imaginary part that is controlled by this action. This action is essentially a tachyon that just doesn't care about causality and just escapes the well. And so I match this tachyon action, the tunneling action, to the quasi-normal mode calculation that, again, we can do by throwing a dissipative mode into the Eguchi-Hanson throat. So it all matches at leading order in the temperature, and you get this sort of simple formula, but still there is sort of much more to understand. Okay, so the final thoughts for today are 3. First, well, quasi-normal modes are kind of hard because they live very close to the horizon. More precisely, they live in the photon ring. I hope I sort of convey that idea. And are hard to match if you want to actually understand it from EFT. We would have some things that add up to this kind of objects. Sorry. That's my Korean text. Anyway, hidden behind the horizon or firewall, so that's where usually the quasi-normal modes are. And there's a 2D gravity interpretation for these quasi-normal modes that have been pushed forward. It's called GT gravity and things like that. And we would actually like to sort of harness the power of these two ideas, EFT on one side and sort of 2D on the other side, and hopefully combine it with multi-loop calculations. And finally, I would like to sort of conjecture perhaps that self-force calculations actually are more natural if you consider a net charge. Yes, because of the reason that these diagrams here that are like these multi-quantum amplitudes with many exchanges actually appear only when you go slightly beyond the self-dual point. So if you were to add a net charge in this diagram, you will find that the sort of coupling only happens when you allow for negative helicity gravitons. So it looks like something that will be suppressed by this combination. So it might have something to do with what people have been doing here in regards to self-force calculation, but at the time I'm not sure. What I'm sure is that we can literally work it out using self-dual actions and perturbing away from self-dual points. Okay. So I already gave away my punchline, but thank you so much.